And from now on, we are going to slightly change the gear, and we are going to start talking about the rotation, okay? And I can tell you guys, rotation is like so far we have dealt with linear motion. Let me write down. Linear motion and a rotational. And these have almost one-to-one matching, okay? So many things that you have learned from linear motion, it's gonna be just translated into a rotational term, and we analyze that having some new terms introduced, okay? So I really want you to make sure that we are understanding this linear motion. Otherwise, if we add more terms from this rotational thing, it's really gonna make you confused. Okay, so I will try to show as much as possible of these one-to-one matching. That way, your basic knowledge that we gain from the physics course and from our course so far in the linear motion can be easily translated into this rotational motion. Okay, so we talked about the linear momentum, right? And now we are going to talk about the angular thing. And the angular momentum is defined as, say, if there's a particle, it's just moving like randomly like that. And if you take a snapshot of it, and if it were having a velocity like that, then the angular momentum at that moment is going to be defined as, we have a term h, it's a vector with respect to a certain location. Say it's O in this case, and that is going to be the position vector R times, it's a cross product, mv. And this is a vector that is perpendicular to the plane containing R and mv. Okay, so we just first talk about this definition, and if we draw that thing on the surface, say there was a surface like this, that surface contains both the vector, position vector, and your velocity, okay? And then this angular momentum is going to be a vector vertical to this surface, okay? And let me just draw that thing. So, okay, so this is going to be your H, and it has a direction like that. And this H is perpendicular to the surface that you are right now. So it's perpendicular to the position vector, and it's also perpendicular to your velocity. So that is perpendicular to this whole surface that contains these two vectors. Okay, and this guy is a cross product, and for cross product, you might have learned this right-hand rule. I wish you guys were all here so that I can really show you my hand, how we do that, but unfortunately, we don't have that kind of luxury. It became like a luxury now. And we don't have that here right now. So I drew a cartoon, and I hope this really helps. But so step number one is your right hand should be pointing from the original towards the particle. Okay, so this is your right hand. Your right hand, your fingers, like those are pointing from the origin to the particle. Okay, and then step number two is you curl your fingers towards the vector and the velocity. Okay, and then the direction your thumb is pointing up, right? In this case, then that is going to be the direction of your cross product. Okay, so this is your right hand rule, and this is going to be very often used from now on when we talk about these angular or things that is rotating. Okay, so make sure that you know how to find the vectors that is coming from the cross product. So two vectors, this and that, are being cross producted, and that creates another vector which is perpendicular to both of them. Okay, and the way you find the direction, whether direction is you again are your fingers pointing like that, and then from there you curl your other fingers towards the next vector, which is velocity in this case, and then you find where your thumb points out, and that is going to be the direction of your cross product. Okay, so we can put some notes here. This angular momentum h is a vector. Okay, it's not a scalar, and as r or mv increases, your angular momentum also increases, of course. Okay, so if there's a particle, if I just copy this, or say here's a particle here, and it has the same velocity like that, then the angular momentum for this particle is going to be smaller than the particle here, because the r vector is going to be smaller compared to the previous case. Okay, so now this angular momentum is not only depending on the velocity itself, but it's going to be dependent on the r vector as well. And we want to find the relationship between the moments of force and the angular momentum. Well, for me, this kind of term was confusing. Maybe not to you guys, but it was to me, because we talk about momentum and moments, and aren't they the same thing? It felt like that to me. So I just wanted to clarify this part for you, just in case you have any, you feel similar to what I did a long time ago, even these days too. So the moments of force is the torque, okay? And what we want to find is the relationship between the torque and the angular momentum. And this is kind of similar to force versus linear momentum. Okay, so this is kind of equivalent to what we're trying to do right now. Force and linear momentum, it had that impulse kind of thing, right? So we're trying to find that thing here. And this moment of forces, the moment of a whatever vector field n at a position r is equal to r cross product n, okay? And torque is kind of subset of a momentum. That torque is a special case of where the vector field happened to be the force, okay? So torque is a moment of force, okay? So these two can be used as the same word. Some, and in physics, they want to divide the term, but well, to me, I think these two are going to be the same throughout this course, okay? So if I write this down, for the linear case, we have dealt with sigma F equals ma, right? And we also talked about the linear momentum, right? That is mv. So the relationship between the force and the linear momentum is sigma F equals L dot. You see the relationship between these two? Because think about it. A is V dot, right? And you have M multiplied in both cases, and this is force, and this is nothing but dot. You see? Maybe I'll put this thing down here. So we want to just do the same thing for the angular things. Summation of moments of force, or which is the torque, summation of the torque, the moments of force is defined by R times summation of F, right? That's torque. And that is R times cross product of MA, right? We're just following the definition of torque, right? And that is a same one-to-one matching with the force in the linear case. Okay, so these two are one-to-one matching. And we just learned about the angular momentum. And this is the linear momentum, right? Maybe I'll just write this down, everything. So momentum, and this is force, this is torque, and this is also momentum, right? Torque is like the force in the angular space. Got that? So this guy is, based on what we just found out, it's mv. So what's going to be the relationship between the torque and momentum, or the moments of force and the angular momentum? That's going to be similar to what we got here. It's going to be summation of all the forces. Torque that is applied is going to be your angular momentum dot. Because it's the same thing. It's V and it goes to A, what we just did here, right? So this is nothing super new. It's just a slightly different version of the things we found from linear, okay? So, well, I will really try to, make these one-to-one matching, okay? And the reason why is I don't want you to think these as like a new, totally new kind of concept. It's just a slight extension from what we got in the linear space, okay? Okay, so the resultant moment about a point O for all the forces acting on that particle. And so that means this thing is the sum of all torques, right? Is equal to the rate of change of particles, angular momentum about 0.0. That's just this thing we wrote down in English. Okay, it's the same as the summation of all forces. That's the change of your linear momentum. Okay, so any question you have? Okay, so let's move on to the next page. Ooh. Oh yeah, I thought it was a totally blank one. Okay, so here I would like to, just write down, kind of summarize what we did for the linear and find the one-to-one matching of the things in angular. So the summation of force F equals ma. We got that, right? This is Newton's second law. And what else did we get? We also had L, the linear momentum is mv. That's just linear momentum, right? And I just showed you that it's ddt of L. Just this from the previous page, right? And let me just write that down like this here. And then from here, what we can do, we can move this t to the left and do the integral. So we do the integral f dt, and that is going to be integral dl, right? And that's what? That's L2 minus L1, and that's mv2 minus mv1, right? So that's what we know, plus equal this guy, the impulse momentum kind of thing. This is impulse momentum, right? And if the summation of force is 0, in other words, no external forces, then what? This guy just goes away, right? So we talked about the conservation of momentum, mv1. If there were even multiple particles, that's the same, right? So these are actually all we kind of learned. This, and that. And let me just write that. This is conservation of momentum. Got that? And we have the one-to-one matching of this for the angular space, angular motion, it has, let's change this to a slight different color. So the summation of all the moments of force, or that's the torque, this is just R times summation of force, and that's R times MA. Right? This is just a definition, okay? So, but in the angular space, the summation of all forces equal MA, and that's the summation of all torque is R times MA. Okay? And we also just learned about this angular momentum, that is R cross V. Angular momentum, right? And if we do the same thing we did for the linear momentum, let's do that. So summation of all torque is what? D dt of angular momentum, right? And we move this thing towards the left and do the integral. And if I just write that down, integral of all the angular momentum dt is going to be d h naught, right? And that's h2 minus 1. So we can also write that the angular momentum at time 1 plus the angular impulse, summation of all the torque that is applied is going to be the angular momentum in time 2. All right? And if the summation of all the torques or angular momentum, the moment of force is 0, or there's no external torque, then what happens? This guy goes away. So that's the same. It's the conservation of angular momentum. So is there a better color? Maybe use this one. Are they going well? Yeah, it's not too bad. Okay, so I hope this kind of clarifies. They are really just one-to-one matching. There's no new concept introduced. It's just they're using the angular force or angular momentum. Angular force is the torque, right? Those to do the same thing as we did for the linear part. Okay, so like again, I really don't want you to think these as a totally new, different creature. It's just a slight extension from the linear to the angular. Okay, so as far as you have a nice concept here, then translating from linear to the angular, you need to practice, and you need to get used to this kind of new space, but it's not a totally new thing. It's just a slight transition from one to the other, okay? And here's a small cartoon. You know, when you have the angular momentum is going to be conserved. Like for example, if I just like that, R times mv is going to be R times mv, right? R times mv, that's the angular momentum, right? So the angular momentum of before and after are going to be the same. So if you have the R that is large, so your particles are kind of far from your center of axis, then your rotation speed is going to be relatively small. But if you keep your particles close to your rotation of axis, where this R is small, then your V velocity, this rotation speed, is going to increase because we want to make these two the same, assuming there's no external force or assuming there's no external torque applied. Say you are on the ice or something, you know, ice figure skating, you see this, okay? So it's just the same thing happening. Let's move on. Again, this is from now on, we're going to introduce these kind of angular thing, and yeah, this moment is kind of important. Like today, and probably next few lectures is going to be pretty important. Okay, so if you have any questions, let me know or shoot me an email or come to my office. I really want to help you guys. Okay, because this is kind of the moment when students, including myself, feel, oh, this thing is so complicated and difficult and start to fail. So yeah. Okay, so let's assume that there are two identical 10-kilogram spheres like this, and the rod is subject to a couple moment that is applied by something in here. Maybe you turn it, or there's a motor or something like that. Okay, so this is providing a torque continuously. Okay, and that is 8 times t. That t is in seconds. And the question is, find the speed of the spheres when t equals 4 seconds. And it starts from rest. And there is no gravity in this direction. Gravity is going into this surface, okay? So gravity is like a vertical thing. So we can just apply what we learned, the conservation of angular momentum. And that is summation of 1 plus is summation of 2. All right? And it said it starts from rest. So we don't have any of that here, right? And we can just do 0 to 4. Your momentum is the moment of force or torque. You see, I continuously get confused about this momentum and moment. Okay, so the torque is 8t dt, and that is going to be R cross mv, right? And because these are all perpendicular, we can just do what? 0.5 times mv. M is 10 kilogram, times, what's V? V is what we want to find out, right? V, right? And because we have two of them, we have to put 2 there because it's a summation of all angular momentum. So we just found the angular momentum of this guy here. The length is 0.5, and the velocity we don't know. The mass, it's given as 10 kilogram, and we have 2 of them, so we just multiply 2. So if you just do the math, this is 4 times 4 squared, and it's gonna, oh, I just forgot about one part here. My apologies. This is going to be actually plus from 0 to 4, 2 times 10 times 0.5 of dt. Like that. Because we also have these masses, right? And that is going to be continuously applied to this point here, right? So we have that term there. Okay, so if we solve the equation, squared plus this is 2, it's 2 times this is 5, and we have 4 seconds, so 2 times 5 times 4 seconds is going to be what? It's these 2 go away, and it's 10 V. So V is going to be 10.4 meter per second. Okay, so we just have applied this conservation of angular momentum, and we can find the velocity like that.